discussed Inception V1 and version 1, and before that we discussed VGG 16, and before that we discussed LXNet. So we also discussed that what's the difference between different versions of pre-trained CNN. So several pre-trained CNNs are available, and they are different from each other with respect to architecture. And as we discussed yesterday, AlexNet was the first pre-trained CNN, which was proposed in 2012, and gradually several versions were proposed every year. So VGG 16 and most of the pre-trained CNNs, they have different versions like VGG 16, VGG 19, which are the versions of VGG. Then we started discussion of Inception, because this is to overcome some limitations of VGG. So if you remember, we discussed that it was observed by the researchers of this Inception model that they observed, like they proposed a new architecture, and for proposing this new architecture, they observed that because of huge variation in the location of the information in image, choosing the right kernel size for convolutional operation becomes tough. Now remember the architecture of convolutional neural network. We have convolutional layers where we perform convolution operation. And to perform this convolution operation, we need kernel. And if you remember, in our example, we used kernel of size 3 cross 3, then 5 cross 5 too. Okay, so choosing right kernel size is tough. Moreover, it was also observed by them that a larger kernel is preferred for information that is distributed more globally, and a small kernel is preferred for information that is distributed more locally. In addition to this observation, it was also observed that very deep networks, because in previous versions of this pre-trained CNN, before this inception net, what researchers were doing, they were increasing the number of layers in CNN. So this authors of Inception Net, they observed that very deep networks are prone to overfitting. And it is also hard to pass gradient updates through the entire network if the network is deep. Moreover, they observed that naively stacking large convolutional operations is computationally expensive too. So to overcome this disadvantages of previous versions of pre-trained CNN, they proposed Inception network, and the solution they proposed in Inception network was they thought of using multiple filters with variable sizes in the same level. So the network essentially would get a bit wider rather than deeper. So earlier versions of pre-trained CNN, they were deeper, while Inception network was wider rather than deeper. So the authors designed the Inception module to reflect this idea that it should be wider rather than deeper. And we discussed, you can see in this figure that this is one module, this is from red to green, it represents one module. Okay, so there are such several modules, and if you remember, we counted these modules too. Such 9 modules are there. Okay, so this is how Inception network version 1 was proposed. Okay, now after that, Inception Net version 2 was also proposed. There are in fact 4 versions of Inception network. So Inception version 2 and Inception, I'm sorry. This was proposed with this hypothesis, Inception version 2. So Inception version 2 and Inception version 3 were presented in the same paper, which was proposed, in which Inception version V1 was proposed by them. So author proposed a number of upgrades which increase the accuracy and reduce the computational complexity. Inception 2 is based on this hypothesis. reduce representational bottleneck. It reduces representational bottleneck. And the intuition was that neural networks perform better when convolutions did not alter the dimensions of the input drastically. Input, like we feed input images. So convolutions did not alter, like it was observed that neural networks perform better when convolutions, like convolutional layers, do not alter the dimensions of the input image drastically. So reducing the dimensions too much may cause loss of information. So it should not be reduced much. So observation was, if the dimension of input image is reduced too much, then there may be loss of information. So dimension should not be reduced too much. Okay. And this is known as representational bottleneck. This problem is known as representational bottleneck. So, okay, so they wanted to overcome this, that what should be done so that dimension of input image does not get reduced too much, because when it is reduced too much, it there may be loss of information. Moreover, they also observed that using smart factorization methods, these were the two observations. One was regarding reduction in size of the input image, and the second was regarding factorization method. So they observed that using smart factorization method, convolutions can be made more efficient in terms of computational complexity. All convolutional neural networks, they are highly expensive in terms of computation. So in every effort, like in every new pre-trained CNN, the effort was made to reduce the computational complexity. So they also thought of reducing this using smart factorization method. They observed that if smart factorization method is used, then computational complexity can be reduced. Okay, so these were the two observations. And based on these two observations, the solution proposed by them was uh, uh, a new inception network, which was inception network version 2. So what they did, they factorize 5 cross 5 convolution, which is used in, I'll show you in architecture. Here you can see that. See this in inception. Yeah, here only you can see this. This is 5 cross 5 convolution in the block of inception network version 1. So what they thought of, that fact this 5 cross 5 convolution should be factorized to two 3 cross 3 convolution operations to improve computational speed, that is to reduce the computational complexity. Okay, so two 3 cross 3 convolution, this is like factorization. And although this may seem counterintuitive, a 5 cross 5 convolution is 2.78 times more expensive than a 3 cross 3 convolution. So they experimented, they calculated the gain, and it has been observed that 5 cross 5 convolution is 3.78 times more expensive than this 3 cross 3 convolution. So stacking two 3 cross 3 convolution, in fact, leads to a boost in performance. So they suggested to use two 3 cross 3 convolution operations instead of this 5 cross 5 convolution. And this is this change is made in the architecture of Inception network version 1. So this is Inception version 2. Okay. Now, they also observed that they factorize convolutions of filter size n cross n to a combination of 1 cross n and n cross 1 convolutions in general. So like several combinations were tried by them, but I am not discussing like depth of this Inception version 2. You can later go through it, that how different combinations can be tried, like different factorizations can be tried. Okay. Okay. Then Inception version 3 was proposed by them in the same paper. They proposed several architectures, and they are Inception version V1, V2, V3. Right. But I'm not going in much details of all these networks. Inception version V3 was proposed because authors observed that auxiliary classifiers. Auxiliary classifiers did not contribute much until near the end of the training process when accuracies were nearing saturation. So they argued that they function as regularizes, especially if they have batch normalization or dropout operation. So this was their observation. Yeah, in addition to this, they observed that possibilities to improve on the inception V2 without drastically changing the modules were to be investigated. So they wanted to do this. So this was their assumption. This was their hypothesis, and based on this, they experimented and they proposed inception net V3. Now, based on this observation, what changes they made in Inception version V3? Inception version V3 was incorporated all of the upgrades of Inception V2 in addition to these features. Now, here you can see the features. The additional features are RMS prop optimizer was added. Now remember the optimizers we discussed. So RMS prop optimizer was added in this Inception network version 3. Factorized 7x7 convolutions. So now here you can see that earlier they suggested to factorize 5x5 and it was replaced by 3x3. But in this Inception version 3, 7x7 convolution was used. Batch normalization in auxiliary classifier was used, and label smoothing was used, which is a type of regularizing component added to the loss formula. So they made several changes in different versions and they experimented, and with every version they observed some benefits. So every version has pros and cons, okay, with different architecture, but they experimented several combinations in architecture. And not only this Inception version V3, they also proposed Inception version 4. So what was there in Inception version 4 and what was the motivation for this Inception version 4? So Inception version 4 and Inception ResNet, it is also available. One apart from Inception version 4, one more version of Inception is available, and that is Inception ResNet. So this Inception version 4 and Inception ResNet, they were introduced in the same paper. And let me tell you that what was the observation or what was the hypothesis. Make the modules more uniform. They thought of making different modules of Inception uniform. The authors also noticed that some of the modules were more complicated than necessary. So they thought to reduce the complications of those modules. And this can enable us to boost performance by adding more of this uniform modules. So this was their observation, and based on this they proposed Inception version 4. I have not included architectures of all these different versions of like Inception V2, V3 and V4 because they are very big, and if I would have included them in this slide, then you would have been able to see only small numbers, very tiny numbers may not be visible to you. So I thought you will explore later. So I have not included those architectures here because they are very big. Fine. So then the solution proposed by them was the stem of Inception version 4 was modified. The stem here refers to the initial set of operations performed before introducing the inception blocks. So they were introduced, and the ResNet architecture, ResNet, even for Inception ResNet version 1 and Inception ResNet version 2 are available. So several variants of this Inception are available, but we are not going in that much detail. Later in later years, if you are working on some project using deep learning or using pre-trained CNN, you can go in depth if you are planning to use Inception pre-trained model, right? It is required to go in deep if you are planning, like if you find model suitable to your project, right, then you should go in depth, you should understand architecture, so that accordingly you can set the hyper parameters for that model. Okay. So I'm not discussing now that ResNet version 1 and ResNet version 2. This information is sufficient for you for Inception Net. Okay. So some slides are hidden by me for all these architectures, because I feel that it would be heavy for you at this level, because you are second year or third year students. So that may be heavy for you. Okay, so now let us discuss the next pre-train model, which is ResNet. This is also very popular pre-train model. So in 2000, this was proposed in 2015, and in publication, Deep Residual Learning for Image Recognition. This is the title of that publication. And this is the work proposed by uh, 4 authors, and they created a particular kind of neural network, which is known as ResNet or residual network. It is residual network. The ResNet stands for residual network. So every consecutive winning architecture, I told you that every year challenge is organized and one model wins. So every consecutive winning architecture uses more layers in a deep neural network to lower the error rate after the first CNN-based architecture, which was AlexNet, which was AlexNet won the ImageNet 2012 competition, right? So after that, subsequent models, they were increasing the number of layers in neural network to lower the error rate. That was the purpose. This is effective for smaller number of layers, but when we add more layers, a typical deep learning issue known as the vanishing gradient. A typical deep learning issue which is known as vanishing gradient or exploding gradient, it arises. And this results in gradient becoming zero or being overly large, either zero or overly large. Therefore, the training and test error rate similarly increases as the number of layers is increased. Okay, and this figures, you can see in these figures uh, that 20 layer CNN architecture performs better. Here you can see that two architectures have been like performance of two architectures have been plotted, 20 layer architecture and 56 layer architecture. So you can observe that 20 layer CNN architecture performs better on training and testing data sets than a 56 layer CNN architecture. So this assumption is not right, that if we increase the number of layers in CNN, they will help us to decrease the error rate. It's not always. The authors came to the conclusion that the error rate is caused by vanishing or exploding gradient after further analysis of error rate, after certain number of layers in the architecture. Okay, and a novel architecture called residual network was launched by Microsoft research experts in 2015 with proposal of ResNet. So who proposed ResNet? Microsoft research expert. They proposed this ResNet. Okay, so here you can see the architecture. So what is this ResNet? The residual blocks idea was created by this design to address the issue of vanishing gradient. A method is applied known as skip connection in this network. Authors applied a method which is called skip connections. Now understand the skip connections, because all latest uh, deep models, deep learning architectures, which are encoder decoder based architectures, they use the skip connections. So the skip connections are significant. Okay, so the skip connections, they applied skip connections in this network, and the skip connection bypasses some levels. They skip some connections. That's why their name is skip connection. So the skip connection bypasses some levels in between to link layer activations to subsequent layers. And this creates a leftover block. This leftover blocks are because some layers are skipped. So this creates a leftover block. And this because they are skipped. So this leftover blocks are stacked to create resonance. So I show you here. Okay. Uh, Fine. So the strategy behind this network is to let the network fit the residual mapping rather than have layers learn the underlying mapping. So let the network fit instead of using, say, the initial mapping of function h of x. So here you can see that function h of f, function f of x is function h of x minus x, which gives h of x is equal to f of x plus x. So here, like in a right side diagram, you can see how it works. X is given as input, weight layer, then ReLU. So f of x, then again weight layer and f of x plus x, like you can see that how it happens. So a skip connection. So this right side figure shows skip connection, or you can say it shows shortcut. It shows shortcut. So the benefit of including this kind of skip connection is that regularization will skip any layer that degrades architecture performance. So which layer should be skipped? Layers which degrade architecture performance. As a result, training can, okay, now how to decide which layer? So this is done always based on experiments. Okay. So randomly you cannot choose layers to be skipped. It is chosen based on the experiment. So regularization will skip. Yeah. So as a result, training an extremely deep neural network is possible without encountering issues with vanishing or expanding gradients. So the very popular data set, the Cypher 10 data set, 100 to 1,000 layers were used for experimentation by the authors of this paper, who were from Microsoft research department. And similar technique exists under the name highway networks, which also employ skip connections. So these skip connections also make use of parametric gates, and the amount of data that flows across the skip connection is controlled by the gates. So this is how the ResNet looks. This is the architecture, and you can see several skip connections. Different blocks are there. So this is the overview of this ResNet 34 architecture. ResNet also has different versions. I'll discuss later, but these are like 34 layers are there. So this is ResNet 34 architecture. But ResNet 50, ResNet 101, several versions of ResNet are also available. Okay. So, but the main idea is to overcome the problem of vanishing gradient, skip connections are used. That is only the distinguished characteristic of this ResNet. Okay, so these are the salient features of ResNet architecture. Okay. The features are, with a top 5 mistake rate of 3.57%, ResNet won first prize in classification competition in 2015. Okay, a model ensemble. Won first prize in categories of ImageNet detection 2 and ImageNet localization, COCO detection, and COCO segmentation at the 2015. So these are the names of different challenges, so COCO competition, and so you can later search about these challenges. ResNet 101, I told you that different versions of ResNet are available. Okay, so ResNet 101 is used in faster RCNN to replace the VGG16 layers, and they noticed a 28% relative improvement when they replaced VGG16 by ResNet 101. Moreover, networks of 100 layers and 1000 layers that are well trained are available through this, due to this research. Okay. So these are the salient features of ResNet. So why do we need ResNet? So we stack extra layers in deep neural networks because we stack extra layers in deep neural networks, which improves accuracy and performance. And often in order to handle a challenging issue, it is useful. The idea behind layering is that when additional layers are added, they will eventually learn features that are more complicated. For example, when recognizing photographs, the first layer may pick up on edges, and the second would pick up on textures, and the third might pick up on objects, and so on. However, it has been discovered that the conventional convolutional neural network model has a maximum depth threshold, and percentage of errors for training and test data for a 20-layer network and 56-layer network. You can see the in the previous graph I demonstrated. Okay. Here you can see the different versions of ResNet. Architecture of this also I have not included here, graphical architecture of ResNet, because it is very big diagram. So if I would have included in slide, then you would have not been able to see numbers properly, because it's a big diagram, including this many layers. So here why I have written ResNet using Keras, purposefully I have written, because you can implement this ResNet and other pre-trained CNN models using Keras. Keras is very popular Python library to implement this pre-trained CNN models. So an open source Python-based neural network framework library called Keras may be used with TensorFlow, right? It is useful, and it is made to make deep neural network experimentation quick. And these are the ResNet implementations available in Keras. ResNet 50, ResNet 101, C ResNet 152. So ResNet with 152 layers is also available. Okay, and ResNet 50 version 2, ResNet 101 version 2, ResNet 152 version 2. Yeah, I'll send you, I'll send you a link of diagram, or when I will share this PPT later at the end of module 4, I will include graphical representation of this architectures in slides. So you can copy and paste in Word file, and you can see what is the difference between architectures of different pre-trained CNN. So I'll surely include it in PPT or in material, in notes. I will include it. Yeah, it is good. I think it is good to include in notes rather than in PPT. Okay, so ResNet, for all these models which I have included on the slide, version 1 and version 2 is available. So version 2 and the original version 1, they vary primarily in that version 2 applies batch normalization before each weight layer. That's the difference between version 1 and version 2. Okay. So after this ResNet, let us now discuss MobileNet. Okay. So so far we have seen several architectures. We have seen LXNet, we have seen VGG16, then we have seen InceptionNet, then we have seen ResNet, and now we are discussing MobileNet. Okay, after this. Fine. So MobileNet, let me tell you how it differs and what is the primary difference between MobileNet and its previous between MobileNet and previous versions of pre-trained CNN. MobileNet is simple but efficient and not very computationally intensive convolutional neural network. So this is the key characteristic of this model, that it is not computationally heavy. Okay. For computational neural networks for mobile vision applications, because this was its name is MobileNet because it was specifically designed for mobile vision applications. MobileNet is widely used in many real world applications, which includes object detection, fine grained classifications, face attributes, localizations, and so on. So, what exactly the MobileNet is? MobileNet is TensorFlow's first mobile computer vision model. It is TensorFlow's. Do you know who has proposed this TensorFlow? Any idea? It is Python library, but who has proposed this TensorFlow Python library? Any idea? It was proposed by Google team in 2015. Okay, so this now it has been almost 8 years, and this is very popular library. Even Google's several applications are built using this TensorFlow. And on top of this TensorFlow, we have Keras. So MobileNet is TensorFlow's first mobile computer vision model. It uses depth-wise separable convolutions. Okay, now see what is difference in this. It uses depth-wise separable convolutions to significantly reduce the number of parameters compared to other networks with regular convolutions and the same depth in the nets. So this results in lightweight deep neural networks. This results in lightweight deep neural networks. The purpose was to create lightweight deep neural networks because for resource constrained applications, we cannot have uh, deep neural networks which are heavy in computations. We need lightweight deep neural networks, not on like resource constrained applications. So all sensor applications, sensors are also limited. Sensors also have limited power. So there are several applications wherein we have limited computing resources and we need lightweight deep neural networks. So a deep-wise separable convolution is made from two operations mentioned here: depth-wise convolution and point-wise convolution. See, there's two different convolutions, depth-wise convolution and point-wise convolutions. So MobileNet is a class of convolution neural network that was open sourced by Google, and therefore, okay, now remember, ResNet was proposed by whom? Microsoft. MobileNet was proposed by whom? Google. And that's why वो TensorFlow के साथ आया, because TensorFlow was proposed by whom? Google. So MobileNet is a class of convolutional neural network that was open sourced by Google and therefore provides an excellent starting point for training classifiers that are small and fast. Okay. So the speed and power consumption of the network is proportional to the number of multiple accumulates, which is measure of the number of fused multiplication and addition operations. Fine. So this is very useful, as I have told you, for classifiers which are very small and fast. Okay, so MobileNet depth-wise separable convolution, how it works. Here you can see that depth-wise convolution and point-wise convolution, these are used to significantly reduce the number of parameters. Why? Okay, I hope you are with me. I told you that convolutional neural networks, they have several learnable parameters. They have several trainable parameters. Okay. And I also told you that if you increase the number of layers, these parameters increase. So, and these parameters are sometimes in crores. Like you can later experiment. I assume that you are performing experiments in lab, and if you experiment any of this pre-trained CNN, please check the number of trainable parameters. So if you see the number of trainable parameters for ResNet 101, it is in crore. And this many parameters are there. And if this many parameters are there, of course, we cannot use this pre-trained CNN with resource constrained devices. Okay, so the purpose to propose this mobile net was to significantly reduce the number of parameters so that computation will be reduced. If parameters are less, then definitely the computation would be less. So for that, they proposed depth-wise convolution and point-wise convolution. Now, how this depth-wise convolution work? So this convolution originated from the idea that filters, depth and spatial dimension can be separated. Filters depth and filters spatial dimension can be separated. And thus the name was separable. Depth-wise separable convolution. The name was depth-wise separable convolution. Why is depth-wise separable convolution? Because it was observed by them that filters depth and spatial dimension can be separated. Okay. Here, like I can explain you with the example of Sobel filter, which is used in image processing to detect edges. You can separate the height and width dimension of these filters. You can separate the height and width dimensions of these filters. Okay. So filter can be viewed as a matrix product of like, okay, I have not included example. Otherwise, I could have included one example with, dimensions of features and dimensions of these filters and all. But this is like here, the two things are separated here. When we use this depth-wise separable convolution, we separate depth and spatial dimension. So we can say that we separate the height and width dimensions. Okay, fine. And the same idea applies to a separate depth dimension from horizontal, which gives a depth-wise separable convolution, where we perform depth-wise, depth-wise convolution. Okay, now depth-wise separable convolution is a depth-wise convolution followed by a point-wise convolution. This depth-wise convolution is followed by point-wise convolution. How it is followed? So depth-wise convolution is the channel-wise spatial convolution. And suppose we have 5 channels, then we would then have 5 spatial convolutions. Okay. After that, point-wise convolution is the 1 cross 1 convolution to change the dimension. It is 1 cross 1 convolution to change the dimension. Fine. So this is like depth-wise is a map of a single convolution on each input channel. And this depth point-wise is followed that convolution. Okay, but remember that point-wise convolution is a convolution with a kernel size of 1 cross 1. That simply combines the features created by the depth-wise convolution. Okay, so that is only the purpose. Okay, fine. So that is about the mobile net. And what are the advantages of mobile net? As you can see here, mobile net are a family of mobile first computer vision models for TensorFlow. It's a family of mobile first computer vision models for TensorFlow designed to effectively maximize accuracy while being mindful of the restricted resources for an on-device or embedded application where we have limited resources. So mobile nets are small, low latency, low power models. Mobile nets are small, low latency and low power models parameterized to meet the resource constraints of a variety of use cases. And they can be built upon for classification, detection, embedding, and segmentation, like all computer vision tasks, different tasks of computer vision. Okay, so they can be used for them. And here you can just like to give you, this is MobileNet version 2. I have not included architecture of MobileNet version V1 because it is very big diagram. So I'll include it in notes, but I have not included it here. but this is a reduced size. Okay, so MobileNet version 2, all the architectures, they can be presented diagrammatically or they can be presented in tabular form. So when we present them in tabular form, each uh, each row gives us idea of layer, like parameters related to one layer. And on right side figure, you can see that how depth-wise convolution filter, it differs from a standard convolutional layer. So, okay, but here, like I told you that they are separated, depth and width, they are separated. Okay. So this is about the MobileNet architecture. Okay, so this is all about the different pre-trained CNN models. I told you that there are many. MobileNet was proposed. We discussed that this was proposed many years back, and we have not yet discussed all the latest pre-trained CNN models, right? But this is enough. Like you have got basic knowledge of earlier versions of pre-trained CNN. Now, if you understand this earlier versions, then you can definitely understand the recent versions of this pre-trained CNN, and they also differ with respect to architecture. Okay, now the next topic in your syllabus is the two topics are left. The one is data augmentation and dropout and normalization and all. But I'll not be discussing dropout and regularization because we already discussed them. So we can discuss data augmentation in deep learning. So let me give you a brief idea. I have not included those slides today, but I'll give you brief idea today about the data augmentation. And in next class, we will discuss data augmentation in detail. So let me tell you that why do we need to augment data? So if we don't have pre-trained CNN, then we need to train CNN from scratch. Now, for many real life sectors, we have limited data. If it is a new problem which we want to computerize, then we may not have sufficient amount of data. And if we do not have sufficient amount of data, we cannot train CNN. Like we cannot train CNN to make accurate predictions. Okay, so that's why data augmentation is required. So data augmentation is a technique of artificially increasing the training set by creating modified copies of a data set. Okay, so I think I can stop presenting slides because I have not included this, but I will discuss about this data augmentation today. I'll give you a brief idea. Okay, so it is a technique of artificially increasing the training set by creating modified copies of a data set using existing data. So copies are created using existing data, and it includes making minor changes to the data set or using deep learning to generate new data points. So let me first tell you what's the difference between augmented data versus synthetic data. Augmented data versus synthetic data. Augmented data is driven from original data. Please understand this because many times people misinterpret these two words and they use these two words synonymly. But they are not synonyms, okay? Augmented data and synthetic data. Augmented data is driven from original data with some minor changes. And in the case of image augmentation, we make geometric and color space transformations like flipping, resizing the image, cropping the image, we increase the brightness of the image or decrease the brightness of the image. We increase or decrease the contrast of the image. So such space transformations we make in image to increase the size and diversity of the training set. I hope this is clear to you, that how we augment the data. Okay, now synthetic data. What is synthetic data? Synthetic data is generated artificially without using the original data set. It often uses deep neural networks and generative adversarial networks to generate synthetic data. You might have heard GAN models. which is generative adversarial networks. So GAN models and deep neural networks are used to generate synthetic data. While augmented data means we use the existing data and we modify them to generate the uh, more amount of data. So the augmentation techniques are not limited to images. You can augment audio also, any type of data. You can augment audio, you can augment video, you can augment text data and other types of data too, right? So when should you use data augmentation? The point may be, when should you use data augmentation? Okay, so data augmentation should be used to prevent models from overfitting. It should be used the initial as initial training set. It should be used when initial training set is too small. It should be used to improve the model accuracy, and it should be used to reduce the operational cost of labeling and cleaning the raw data set. So these are the purposes of using data augmentations. There are some limitations of data augmentations too, but there are benefits too. So once we augment data, we need to experiment and we need to check whether this data augmentation is improving the performance, or it is performance remain the same, or performance it degrading the performance. Like limitations, let me tell you some of the limitations. The biases in the original data set persist in the augmented data, because when we augment data, we are using the data from the same data set. So biases in the original data set still remain, right, in the augmented data set too. Moreover, the quality assurance for data augmentation is expensive. Okay. Moreover, research and development are required to build a system with advanced applications. For example, generating high resolution images using GANs can be challenging. Okay, it's really challenging generating high resolution images, and several open-ended problems are available on this. And because I know this, because I have collaborated some university across the globe, and we are working on similar problems, like improving. Recently, I posted one open-ended problem related to this, to enhance the quality of ultrasound images, because ultrasound images, they are used in medical domain because they are cheaper compared to other medical imaging image modality, compared to like CT scan and other image modalities. This ultrasound is cheaper, so it is preferred for diagnosis of many diseases, but many times its quality is not good, and if it is not good, then automated diagnosis may not be accurate, right? So we are working it's an open-ended problem, that how to increase the quality of, how to enhance the quality of ultrasound images, so that the diagnosis can be better, the diagnosis can be improved. Okay. Okay. One more limitation related to this data augmentation is finding an effective data augmentation approach can be challenging. So these are the purpose. Okay, we have discussed the purposes and limitations. Okay, now let me tell you which are the data augmentation techniques. Data augmentation techniques and techniques to generate synthetic data are different. Data augmentation techniques and techniques to generate synthetic data are different. Uh, okay, let me tell you that which are the techniques which can be used to, the different techniques are available to augment the data of different types. Data of different types means text data, audio data, image data. So for this different types of data, different techniques are available, different augmentation techniques are available. So audio data augmentation, for audio data augmentation, the techniques available are noise injection, shifting, changing the speed of audio, changing the pitch of audio. These are the data augmentation techniques. Okay, so noise injection means add Gaussian or random noise to the audio data set to improve the model performance. Shifting means shift audio, that is fast forward. Shift means fast forward or right. Shift audio left or right with random seconds. So that is shifting data augmentation technique. So new data will be generated applying this on the existing data. Changing the speed, that is stretch time series by a fixed rate. Stretch time series by fixed rate, that is changing the speed. And changing the pitch means randomly change the pitch of the audio. So these are the commonly used data augmentation techniques for audio type data. Okay, for techniques are word or sentence shuffling. Okay, this you will easily understand. Okay, suppose एक sentence दिया गया है and मेरे पास suppose I am processing the text and मेरे पास limited records है. So what can we do? हमारे पास जो records है उसमें हम क्या कर सकते हैं? Word को shuffle कर सकते हैं. Sentence को सब if paragraphs are there and we are processing paragraphs, तो paragraphs shuffle कर सकते हैं.
Sorry, ma'am. Hello, ma'am.
Yeah.
Ma'am, your PPT is not visible. So, have you stopped the presentation or?
PPT is not visible. Okay. Yeah, PPT is not visible for this because I have not included PPT of this data augmentations in today's presentation.
Okay, ma'am.
Yeah, I am orally discussing this. So next time I'll show you again. But concepts I'm discussing because I know regarding this data augmentation, so I'm orally discussing without PPT.
Okay, no issue, ma'am. Actually, in between that, I was not present in that lecture. That's why.
No, it's okay.
Again,
It's
I have
fine.
rejoined. That's why. Okay.
Fine. Okay, thank you. So we were discussing about the techniques to augment text data. Okay. So text data, I told you that how can we increase the size of data? We have limited text data. So if we want to increase the size of text data, then we can shuffle word or sentences. We can replace words with synonyms. Okay, because you too know, suppose tweets are there. So tweet may suppose there is you want to express the happiness through tweet on some occasion. So some may use like for to represent your emotions, different people they use different words. Okay, so we can replace words with synonyms to augment data. Syntax tree manipulation is also one technique. Paraphrases the sentence using the same word, like then random word insertion, insert words at random. Okay, suppose it is a good suppose the statement is it is a good day, right? So it is a very good day. So random words may be inserted, random word may be deleted also. So these are the data augmentation techniques for text data. Okay, so we have seen some techniques for audio data augmentation. We have seen for text data augmentation. Now let us discuss the techniques for image data augmentation. Image data augmentation, geometric transformations are very popular for image augmentation. Geometric transformations like flip operation, crop operation, you can crop image, you can flip image, have vertical flip, horizontal flip, दोनों possible है. So flip operation, crop operation, rotate operation, stretch operation, you can stretch image, you can rotate image by different angles, you can zoom in, zoom out image. So you need to be careful about applying this multiple transformations on the same images, as this can reduce model performance. Okay, so carefully you have to apply this transformations. Like when you apply crop, so you have to carefully crop it. Okay. The next image augmentation technique is color space transformation. Randomly change RGB color channels. Randomly change RGB color channels, contrast and brightness. So this is also one technique to augment the image data set. Okay. The next technique is kernel filters. Kernel filters means randomly change the sharpness or blurriness of the image. Randomly change the sharpness or blurriness of the image. That is kernel filters, applying kernel filters. Next data augmentation technique is random erasing. So that is delete some part of the initial image, and that is called random erasing. Mixing images, that is fusion. It is called fusion of images. And in healthcare also, this is very popular sometimes when it is not possible for medical professionals to diagnose to locate the object or to diagnose disease from one type of medical image modality. What they do, they fuse two types of medical image modalities, like CT scan and MRI, or ultrasound and CT scan. They fuse these two types of medical image modalities because it helps them to diagnose or to locate the objects accurately, for example, to locate the brain tumor accurately. So that is called mixing image, blending and mixing multiple images. So these are the different techniques for augmentation of image data sets. Okay, and some advanced techniques are also available. Advanced techniques like generative adversarial networks and neural style transformation. Neural style transfer. So they are also available when you want to increase the size of data. So in fact, I have discussed the whole data augmentation technique, whole data augmentation, topic. So I'll show you all these techniques next time, including in PPT, but this is what I wanted to discuss related to data augmentation, that we can augment different types of data. Data may be audio, video, image, text, and different techniques are available. And we have also discussed the difference between data augmentation and data synthesis. Okay, so I hope it is clear to you. Now, if you have any question related to these topics, I would love to answer your questions. And this data augmentation is also available, like with Keras and TensorFlow libraries, you can implement this data augmentation very easily. So if you want to implement this deep neural networks, you learn this TensorFlow first and then Keras, because Keras is built either on TensorFlow or on PyTorch. Like the base model may be, for Keras, the base model may be TensorFlow or PyTorch. But I suggest TensorFlow. So you can learn these models if you want to implement deep learning models. Yeah, so that's all from my side for today. Now, if you have any question, I would love to answer your questions. Okay, let me check in chat box. Okay, so Dia is saying, so AI image generators output synthetic data, and when we edit images, it is augmented data. So when we edit means those operations are also fixed, like they are traditional transformation techniques, image transformation techniques. So when you apply image transformation techniques, that is data augmentation, that is right. And synthetic data means we generate data using AI models. Yes. So when we generate AI models, yeah, using AI models, when we generate, it is synthetic data, because artificial data is generated, synthetic data is generated using artificial models. So that is, yeah, that is true. Any other question?